And this organization really had an interest in understanding the relationship between what goes on outside the mainframe and what goes on inside, because they were having all sorts of challenges managing the load on the mainframe. They were not able to tie together user activity and mainframe load. Now, a complicating factor was that the application that this customer used came from a third party. So it's already a bit of a black box. When we talk to some customers about HTAC, what they're most interested in doing is really achieving end-to-end tracking. So they know that this person using this app on this device, his request was serviced by these transactions at this time, and it cost them Y in resources. And that end-to-end picture lets them see everything required to support that end user and assess the quality of the interaction. Well, in this case, that was important to this company, but they really wanted more. They want to understand what is going on the inside of the mainframe that is causing them to upgrade their mainframe. What is it about this application? What is it about the nature of the requests? And so in order to meet their expectations, we had to really understand how this application worked. And so we interacted with the vendor quite a bit, asked a series of questions, and fortunately they were willing, as long as our questions didn't take too much time, they were willing to tell us and help us figure that out so that we really could understand better about what's going on. This is an interesting diagram because it really does show kind of the end user's environment. So they do in fact have end users, whether they are customers or most likely agents. They do use a middle tier a middle tier application server, and it's running WebSphere. We show here, they have a suite of applications that we show here kind of as the program handling, some end user request. And the way that they communicate to their code running on the mainframe is across sockets. Now, the heart of HTAC is this concept of extraction, extracting data that is relevant to the customer for purposes of either transaction tracking or asking deeper questions, like what is the request that's being serviced? And so we worked with that vendor to be able to mine and understand how that data was encoded as part of the data flow and requesting. One of the things that is interesting about this application is when I log on as an end user, it's going to start a transaction over on CICS called SAPS. Over the life of that session, it's going to start a number of other more specific processing transactions called SAPU. So if I switch over to this dashboard, that's what we're attempting to show, just the first basic correlation. And that is how a single SAPS transaction, so for example, this was just a demonstration environment, so it's low volume, but in that time frame, there were 3 SAPS transactions run. But that's not really an interesting metric, right? What you really want to know is what happened on the main, what are the SAPUs? And what we know is that in that same time frame, with those, it's likely that those 3 SAPSs rippled out into 391 SAPUs. And then using this data, now that we have sitting down in Splunk, we can look at some other things at a very high level, such as the total CPU time consumed by those SAPU transactions. And so we can come down to the same interval and we can say, well, okay, we can't say if it's good or bad, but it was 20 CPU seconds were spent during that interval. And then we also built this dashboard to keep track of the duration. Think of it as the response time, because this system can become so constrained that we want to be able to look at how, as load goes up, does the response time of the SAPU transactions go. So this is just one example of a dashboard that we created to help them begin to visualize what was going on. Now, here's another kind of dashboard that we created. We also built this sort of a panel so that we can actually say, here's the transaction group ID, and what really happened under that. Now, this was one that really was kind of a known problem. I mean, it represented a spike. What happened here? So using Splunk and the data that we've externalized, we just give them a single dashboard to understand about this whole transaction group. For example, when did it start, when did it stop, and what the total duration of the SAPS transaction was. Because again, the SAPS, think of it as holding a session. Well, then how many SAPU transactions occurred under that? Well, it turned out 1,726 individual requests were made to fulfill this session. Their combined duration was 2 minutes and 9 seconds. So the session was idle for about 20 minutes of its life. No big deal, but just something to keep our eye on. Now, then the next thing we can see is, since we have the power of Splunk to kind of visualize things, we can kind of see, well, how did those 1,726 transactions actually occur over time? And you can kind of see. It's kind of, there was something at the beginning, there was kind of a lull in the middle, and then something happened at the end, and every now and then there's some transaction that really takes substantially longer than the others. So now what we want to do is go down and look at other things. Now, this particular application, when an SAPU transaction is run, and that's a work request, we were able to, in conjunction with the vendor, find the data that said what is the work to be done. And that, the way this particular vendor describes the work to be done is as what they call a BC, which stands for a business component, and a method. What is the method? So every work request carries with it a BC number and a method number. And that is the work request along with some data. So what we then said is, okay, it might be interesting to know how often is a particular BC and method combination used, and what's the total CPU time? Where are the heavy hitters, in other words? And which would also, another way to say, where's our low-hanging fruit to optimize? So, and clearly, to find the low-hanging fruit, we just look to the upper right-hand scale, and sure enough, there is a BC whose number is 10075, method number 1. It was used 394 times, and it used a total almost of 37 CPU seconds. There's your heavy hitter, right? You know exactly now through one dashboard for this transaction group what's going on. Here's another one, 3212, method number 1. Not nearly as much CPU time, but a whole lot of frequency. Then I might look over here. Again, the scales here are logarithmic, so they're kind of exponentially higher. Here's one right here. It was only run 10043, method 4 was run 48 times, but those 48 times it consumed 19.5 seconds of CPU time. So through analyses like this, you can begin to see kind of what's going on. We've actually drilled down even further on this because now we know, okay, this is something here is maybe a little expensive. So I'm going to go ahead and get this transaction group ID and just make a copy of it. Ultimately, all of these dashboards will be linked together in a way that makes sense to them. This is a very powerful screen. So I'm going to paste in that transaction group ID. This is one that we're just now developing. And I'm going to say, since this happened a while back, I have to set the time frame back a little bit. Here again, we're now looking at those 1,726 transactions through a slightly different lens, a more critical lens. So we really have our microscope tuned into CICS right here. So we can see the transaction count, we can see the total duration, that's real time. Now let's begin to analyze the duration of those SAPU transactions, right? Well, the first thing whenever you do a duration analysis is a CICS transaction can only be in one of two states if it's in the system. It's either suspended or it's dispatchable. So we can see just from this, we now know that, okay, 16% of the time it was suspended, not bad, and 83% of it's dispatchable. Then we can go over to this panel here. Now, dispatchable transactions are either running, in other words, they have the right to use a CPU, or they're waiting, right? Now, so here we can see, well, okay, of all the time that it was dispatchable, it was about 18% of the time it was waiting on CPU. And conversely, 82% it was running. Okay, that's good. 82% it's running. Let's look and see actually where it was running. Well, it looks like it was running 20% on an open TCB called the L8 TCB, but roughly 80% of the time on the QR TCB. That's where my antennas would go up. It's like, we have an application that is consuming the bulk of its time on the QR TCB. That's always a point of congestion because only one transaction can be actively executing on that TCB at any given point in time. So maybe there's a point of competition there. We'll figure it out. Well, we also said that 20% or 16% of our time was suspended, so let's kind of analyze the suspended time as well. Because you can generally be suspended for two broad reasons. The first is obvious, and that's input and output. And in this case, it was 74%. But there are also other or non-IO reasons, and that was 25% of that time. Then we can break down each of those. Now, this was interesting. Of the IO wait time, when we broke that out, it turned out that 47% of the IO wait time had to do with LU 6.2. Now, this was a great example of as someone going into this site, I need to understand what these applications are doing, or this customer would like to understand what these applications are doing. I didn't know that they used LU 6.2 under the covers. I'm not sure they knew, but sure enough, half the IO wait time is LU 6.2. The other half is interesting. This value called TSIO WTT, the labels are a bit geekish, but what that is saying is that's the wait time related to doing TSQ operations. So, and sure enough, this application, once we looked at it, does a extremely high volume of TSQ operations. So then we can also analyze other wait times, and this was kind of interesting because these are causes of non-IO wait time. And look at this one, 92% is related to dispatcher delay. So 92% of the non-IO wait time is related to something related to the dispatcher. We'll get to that in a minute. Okay, so then we want to see other things that are high-level indications of activity. So these, during this session, an SAPS and all of its dependent SAPU transactions, all 1,726 of them, they in total executed 5.7 million CICS commands. I didn't expect to see a number that big, and I don't think the customer did either. They also executed 780,000 DB2 requests. No MQ, no IMS. But let's go over here to the right side and look at dispatcher delay. We said that we know there's some sort of a dispatching delay going on here. It's the biggest cause of non-IO wait time. And so this is another, if you have a application that is heavily dependent upon the QRTCB and dispatcher delay is your highest reason for waiting, for non-IO reasons, just do the math. 45% of the dispatcher delay time was waiting on the QRTCB to become available. They have so many transactions competing for a single thread of execution, that 45% of the non-IO wait time was just waiting, this transaction, waiting in line for its turn to run a few instructions on the QRTCB. Now, if we go down to this last panel on the dashboard, we just simply kind of showed the highest exec CICS command categories. Clearly, the heavy hitter was TSQ. This transaction did almost 2.6 million exec CICS commands dealing with TSQs. That was an aha moment. Not all CICS commands are categorized, but it's also rather interesting that 1.7 million fell in a generalized uncategorized session. We need to go figure out what that's all about. Some of the ones that you would expect to be resource consumptive, like get main and free main, sure enough, it did 500,000 get commands above the line. It did 420,000 below the line. What's up with that? So these sorts of dashboards let them, as the application owner, now trying to explore this black box, to now begin to ask some really interesting questions about this transaction. So the next step with this customer now is to, using these tools, put them into a deeper testing environment so that they can actually begin to gather more data, and we can begin to not only understand the correlation between end user activity and mainframe resource demand, but also create dashboards on the basis of this data that let them really understand what sort of conversation should they have, maybe with that application provider. The fact is that without HTAC, two things would not have been possible. One is they cannot correlate these requests back to the requester. But then secondly, they would also not know the actual method being run. What is this work? What is this transaction actually doing? Because using in the standard SMF data that CICS would create for a transaction, it would not know that this happened to be a request for business component 10043 method number 4. It just wouldn't know. We knew that, or that data was added to the CICS transaction tracking data by virtue of HTAC. HTAC was the active element in this diagram right here that saw that request come in, intelligently extracted from it the particular bits of data that we needed to do effective correlation and data and request analysis, let it propagate through CICS transaction tracking, and then ultimately find its way, all of the enriched data that we added, find its way to an SMF 110 record and ultimately down to Splunk. So without HTAC, they would not have this kind of actual visibility into the load being created by a given user.